uniformity of our world is explained by inflation. We know why the universe is locally uniform. That's what Einstein wanted to understand. Why the universe is so uniform, and he said, this is cosmological principle. The universe must be uniform, but we did not really know why. So now we know why we see the universe is uniform. But then later we learned that it is uniform locally, but on a much larger scale, like with this football multicolored, the universe is very non-uniform. So the same theory, the only theory that we know predicting, explaining uniformness, the same theory tells you that at a large scale it must be 100% non-uniform. So that's kind of paradoxical situation. And then inflationary universe becomes a multiverse. And this fact that it becomes a multiverse allows us to justify this anthropic principle, which otherwise would be a hateful idea. In fact, it was a hateful idea. When I was in Soviet Union, it was a hateful idea, and there was only one person who was discussing it, and I was going to his seminars because he was a friend with my parents, so I kind of yeah, okay, let me go there. And then, oh my God, he's saying something very, very interesting. But it does not make any sense, because anthropic principle, who gives you these universes? And it's only when we have seen that the universe itself produces itself in all of its possible versions, then we realize that it's a good thing. It is not a metaphysics, it is a possibility. This is how we think about our universe at the moment. So look at this yellow blob from the beginning. This lower part, you would think, this is the moment of creation of the universe. The universe was born in the Big Bang, and then it was expanding, and then if it's closed, maybe it collapses. If it's open, continue expanding forever. Now that we know that you have this non-zero vacuum energy, it is going to expand forever in any case. Okay? So this is the picture which we thought. We thought that our universe is a sphere. This is the best image which Greeks invented. And now what I'm showing you is one of the best images of 20th century. It's fractal. It's a different concept. When you have a bubble producing new bubbles, producing new bubbles, producing new bubbles, and there are some rules which show how from the green bubble you can produce blue and red, how from red you can produce white and green. And so when you learn these rules, you see that the universe eternally reproduces itself, and instead of being one balloon, it is a fractal consisting of balloons producing balloons forever. So one thing is that the universe as a whole is immortal. Okay, so this part may die. Our part is going eventually to collapse or to be destroyed. But in the previous picture, we thought that this is a Big Bang, and here is a place where we live. And then we look at this neck here, and we look at this, and we say, this is the Big Bang, because our bubble was produced at this, okay? But then we say, no, it's actually not a Big Bang. It's a pretty big bang, but not the Big Bang. So this is how we see the situation right now. Does not mean that this is necessarily true, because it's kind of very big leap. We are learning how to interpret it quantum mechanically, because there is a lot of subtleties in it. We are learning how to live, how to make predictions in the universe where there are infinitely many green universes and infinitely many red universes. Because if you want to say it's most probable to live in a red universe, you compare. Here is red universes, and here are green universes. Take one red, one green, one red, one green, one red, one green. Okay, so equal number of them. But you can take one red and two greens, one red and two greens, because there are infinitely many. You can continue counting, and then it will be a problem that you have this indefiniteness. What is more probable? We're learning how to ask questions about this structure. We're learning how to build physics there, and that's a lot of thing to learn. But one way or another, we are trying to just first analyze this cartography of this. This is called Professor's Rubik Cube, okay? So you have much more difficult problem to solve how to arrange it. We are trying to see how many opportunities the universe gives us. And it's not only in terms of string theory, but look, here is a galaxy, here is another galaxy. If we are in a different part of the universe, there would be galaxy, and there would be another galaxy. How many different versions of the observable part of the universe we can potentially see if you take into account not only string theory, but just the same quantum fluctuations which produce galaxies which we see right now. And by the way, this is one of these amazing features. Who thought that galaxies, big boys, okay, can be produced by quantum fluctuations? This is the most well accepted right now, most probable source of creation of galaxies. This is just crazy. So now we're trying to be even more crazy, trying to see how many different compositions of galaxies, distributions of them, and the total number appears to be much larger than the total number of vacua in string theory landscape. So now we may ask a different question. How many different universes a person can observe and remember? And that strange issue is like how many breakfasts can you eat? Or as many as they give us, okay? So nope, there is a distinct boundary. If you have a person with a mass m, there is a quantum bound on the total amount of information which this person can store in itself. So this bound is huge, but still finite. And then if you look at how much your brain can store in itself, it's also a finite number. So this is an interesting story that you have lots of different multiverses, but in the end, it's you who absorbs all of this information and either capable or not capable of using it. This multiplicity in part is bounded by your own existence and by the way how you look. If you were an electron would not be able to experience multiverse. Electron would be unable to have any memory. Because you are large and complicated, then you can enjoy different number of these universes. Strange thing about this picture is that all of these vacua are metastable. What do I mean by metastable? Previously we thought, here is our universe, and there are two ways for us to die. Okay? If this closed universe, for us, many ways, but for the universe. Okay. So here is the universe, and the universe may collapse if it's closed universe, and then all of us die in fire. Okay? Or it expands, well, like an open universe, and all of us die in cold. Now then came these experiments of '98, and people said, here is this vacuum energy, dark energy, whatever, and if it's vacuum energy positive, then the universe is going to expand forever, even if it's closed, guaranteed that everybody will die in cold. They will not die in well, fire. Now with the invention of string theory, we have new versions, okay? So many more ways to die. So here is a funny story. You are standing here, and this is your red universe, and this is your blue universe. Actually, you may not even, well, touch this blue universe. It's further away from you. But this red part where you live is a little bit unstable, and in it, you can produce pieces of blue universe. And then it expands on you and hit you, and you will see this bubble coming on you when it hits you, because it will travel towards you with a speed equal to the speed of light. So I really sincerely hope that I will be able to finish this talk before something hits me. And unpredictable, but it is expected is a theory, okay? Expected that the distance for the probability for this bubble formation is very, very small. We already tested that during 10 to the 10 years, well, 15 billion years from the existence of the universe, no such bubbles were produced. So our vacuum probably is sufficiently stable, or maybe we were just very lucky, but probably it is sufficiently stable. So that is one thing. When this bubble hits you, most probably you go to what is called, well, universe with negative vacuum energy, and then this universe rapidly collapses, end of story. unless you know how to go through the singularity. Now, another possibility that when this bubble comes to you, it transfers you to 10-dimensional space, which is the best place for string theory to live. 10-dimensional space, we would be unable to live there because planetary systems can live only in 3-dimensional space, 3 plus 1, okay? That's a strange fact which was found in 1917 by Paul Ehrenfest. Several things happened in 1917. Great October Revolution, discovery of de Sitter space, and explanation of why our space is 3-dimensional. We cannot live in any space except for 3-dimensional space. Planetary system, atomic system can exist there. So if the bubble comes and your space becomes 10-dimensional, too bad. Now, what is good, however, that because the universe is in this process of self-reproduction, then there will be other places where the universe continue living and producing many of its different copies. When I say all of this, I must say that I'm still internally trembling because all of this depends on our understanding not only of, well, classical physics, but of quantum cosmology. And quantum cosmology is a very dangerous field. Many people made many mistakes, misinterpreting some of these results. So one should be very careful. So I'm just talking about this to the best of my abilities of understanding it, and many other people looked at it and checked it to the best of their abilities. So we're doing our best, and this best is very, very strange. So now, is it physics or metaphysics? And can it be experimentally tested? So that's the standard question which I am often asked about it. And can we actually test this multiverse theory, or it is just a philosophy? Well, so first of all, this theory provides the only known explanation for lots of different questions, like, for example, why this vacuum energy is so small. No explanation if we are given a universe. Okay, so this would be just a chance. We could get a wrong one. But if you have many places, then you live in a place where everything is fine. Why electron mass is so small? It is 2,000 times smaller than the mass of the proton. But if it were 10 times larger mass or 10 times smaller, then life as we know it would be impossible. Why the proton mass and neutron mass are almost equivalent to each other with accuracy better than 1%. If you increase mass of one of them by percent or decrease it by percent, life as we know it, chemistry as we know it, nuclear physics as we know it would be impossible. So these simple small changes in known parameters of our world would totally destroy our possibility to live here. So then now, if you want to understand why we're here, you either should say, oh, God just created exactly for our benefit, or you say, well, this is a multiverse, and in parts of it you can live, and in parts of it you cannot. So then it makes sense. And this is the method which was used by Sherlock Holmes. You know, some people say that scientific principle is the theory must be falsifiable. So how you falsify the existence of these different universes which are unobservable. But there is another principle which was used by, actually which is used every day in the courts. Like, for example, when a man kills his wife, you do not give him another knife and another wife and repeat the experiment to check. Instead of that, you try to exclude all other possible explanations. Then when you reach the satisfaction, then everything else follows. So this is another method which is as scientific as usual. Somehow it is not in the textbook, and we're using it all the time. There is nothing metaphysical in it. And yes, this is a famous, philosopher which said these words. When you have eliminated the impossible, whatever remains, however improbable, must be truth. So this is one thing which helps us with the multiverse. Can we still return back from this picture of the multiverse to the picture of the universe without any of these branches? Well, if you are talking only about inflationary cosmology, yes, it is possible. It's possible that our universe doesn't have many of these possibilities. It's possible that we cannot live in any other places because these other places simply do not exist. But it is like that. If you want to produce a theory which does not have this multiplicity of everything, first of all, you should find an alternative to inflation. Because inflation allows you to have this different distribution of galaxies here and here, because they are created by quantum fluctuations. Quantum fluctuations are unpredictable. You have absolutely different patches of our own universe, independently of the string theory. Second, string theory forces you, in addition, gives you this gift of 10 to the 500, or maybe more, maybe less, we don't know for sure, but huge number of different vacua in string theory. So you must suggest an alternative to inflation, you must suggest an alternative to string theory, and you must also give an alternative explanation to all of these coincidences which we found. So yeah, it may be possible, and then those of us who criticize inflationary theory, my answer to them, any suggestions? Because criticizing, you just open the blog, whatever, and then you read, not even wrong, this is standard blog, which criticizes string theory and inflation and everything, and they criticize. Nobody suggested anything better, which would work, which was shown to work. But criticizing, it's easy. So that is the homework for those who try to do better. Now, to illustrate this, and this will be, well, concluding part of my talk, is something which I learned recently, because I did not know. It was a TV show, what it was, at Bloomberg, and very wise old man was taking an interview with very bright young woman theorist, and she was telling him everything about string theory and extra dimension and everything. And then he said, after, after this interview, he asked, yeah, but Einstein said that the most incomprehensible thing about the universe is that it is comprehensible. And she said, and that was the end. Because you do physics, but you do not have the first idea why physics can even work. Then why do I need even to listen what your physicist said? Because this is Einstein. Einstein did not know how to answer to this question. Then I'm looking at something else, and that is a mathematician. One of the famous mathematicians, Eugen Wigner, and he represented the same idea. The unreasonable efficiency of mathematics in science is a gift we neither understand nor deserve. Oh my God. Okay, so yeah, he is a mathematician. He cannot understand why mathematics is so good. Okay, so then I thought, well, maybe this is an old story and people know better right now. So I looked into modern mathematicians, and this was one of the famous Russian mathematicians who spent his last years of life in the United States, and he have written something else. There is only one thing which is more unreasonable than the unreasonable effectiveness of mathematics and physics, and this is unreasonable ineffectiveness of mathematics in biology. So let's just check what these people are telling us. Something is going on. We do not understand why we can understand. Okay? So now, the reason why Einstein was puzzled is that here is the universe, and somehow everything is good, and the laws of physics actually work here, and you can use these laws of physics to describe it. And then if the universe is everywhere the same, and the laws of mathematics are working here, then it's just, well, God gave you the gift which you neither understand nor deserve. So yeah, but no, we don't want to stop at that. We want to have some idea, even if preliminary. And so in inflationary multiverse, this problem disappears. And well, say disappears, this is my punchy way of saying something which I am a little bit, well, overemphasizing, probably overselling perhaps, but this is how I feel. Because in the multiverse, you may have some parts of the universe where energy density is huge, and quantum fluctuations of space and time are so strong, like Planckian density, like conditions near the Big Bang, so strong that all rulers are bending like that, and all clocks are broken, and memory is impossible, because you record something, but your recorder immediately destroyed. So then, in this part of the universe, mathematics is inefficient. In this part of the universe, laws of physics are useless, because you cannot remember and restore and whatever. There are some parts of the universe where it's just vacuum, and life of our type is impossible because, well, there are no elementary particles which are required for that. So there are many places in the universe where laws of physics are useless, and mathematics is inefficient because there is no memory. Why what we call by mathematics is efficient? Mathematics is efficient. We need it to be efficient because it helps us to win the game of evolution. If we could not predict what we are doing right now, if I could not predict that I'm a little bit, well, like 1 minute ahead after my schedule, then, well, if I would be after my schedule by 1 hour, then I will be killed by organizers. So I need to expect something. I need to calculate something. And we have been, well, successful in our game of evolution because in our part of the universe, mathematics and physics are efficient. And therefore, there are some parts of the universe where mathematicians and physicists cannot live. But there are some other parts of the universe where mathematicians and physicists and all of us can live, and we're just lucky to live in one of these parts. So thank you very much. I finished.